Therefore, in this lecture we find out the length of line segment X. In the drawing we have two quarter circles. Those two quarter circles touch each other at point B. In addition, you know that line segment AB equals to 1 unit in its length. Line segment QS equals to line segment SP. And our mission is to find out the length of this line segment BC that is equal to X. We have to find out the value of X. So first of all, we know that this is a quarter circle, and therefore AB equals to PA. They are both the radii of this quarter circle, therefore they are equal to each other. So AB equals to 1, therefore PA must be also equal to 1 unit in its length. Likewise, in the bigger quarter circle BC equals to QC, they are both the radii of this quarter circle, therefore they are equal to each other. BC equals to X according to what is given as the equation, therefore QC must be also equal to X units in its length. In the next step, we will join points P and B together by a straight line. By joining points P and B, we created the right triangle, triangle PAB. So I copy the right triangle, triangle PAB in a new page, and we will implement the Pythagoras theorem on this right triangle, triangle PAB. Here by PT is the relation for Pythagoras theorem. So actually, this is the right triangle, triangle PAB that I covered from the original drawing. In the right triangle, triangle PAB, according to the Pythagoras theorem, PB square equals to PA square plus AB square. So PB square, that is the square of the hypotenuse of the right triangle PAB, equals to PA square. PA is 1, therefore PA square is 1 square, that is 1, plus AB square. AB is 1, therefore AB square is 1. So in total, PB square equals to 1 plus 1, that is 2. So PB square equals to 2. We'll take a root out of this equation, and finally we get that PB equals to the square root of 2. So here, the hypotenuse PB of the right triangle PAB equals to the square root of 2 units in its length. So here we focus on the right triangle PAB. In the right triangle PAB, PA equals to PB. And we have the rule that in front of equal sides in the triangle there are equal angles. So those two angles that are located in front of those two equal sides must be equal to each other. So if this angle equals to alpha, then the other angle must be also equal to alpha because they are equal to each other. And you also know that the sum of the angles in any triangle is equal to 180 degrees, and especially it is true in triangle PAB. So in the isosceles triangle, triangle PAB, the sum of the angles must be equal to 180 degrees. So which angles we have in the right triangle PAB? We have alpha plus alpha, that is 2 alpha, plus this angle that is equal to 90 degrees. In total, the sum of those three angles must be equal to 180 degrees. Here we subtract 90 degrees from this equation, and we get that 2 alpha equals to 180 degrees minus 90 degrees, it is 90 degrees. Here we divide this equation by 2, and finally we get that alpha equals to 90 degrees over 2, that is 45 degrees. So actually, this angle alpha equals to 45 degrees in its size. And this is also angle alpha that is equals to 45 degrees. we join points Q and B together by a straight line. So, by joining points Q and B, we created the right triangle QCB. In the right triangle QCB, those two sides are equal to each other, therefore it is an isosceles triangle that is also a right triangle. It is exactly like this triangle. If we repeat on the same process on this triangle QCB, we'll find out that those two angles, each of them also equals to 45 degrees. So this angle equals to 45 degrees, and this angle also equals to 45 degrees. In the next step, I will copy the right triangle QCB in a new page. We will implement the Pythagoras theorem on this right triangle, triangle QCB. Here by PT is the evaluation for Pythagoras theorem. This is actually the right triangle QCB that I copied from the original drawing. In this right triangle QCB, according to the Pythagoras theorem, QB squared equals to QC squared plus BC squared. So QB squared, that is the square of the hypotenuse, equals to QC squared. QC is x, therefore QC squared is x squared plus plus BC squared. Plus BC squared. BC is x, therefore BC squared is x squared. So in total, QB squared equals to x squared plus x squared, that is 2x squared. So QB squared equals to 2x squared. We'll take a root out of this equation, and finally we'll get that QB equals to the square root of 2x squared. So it is the square root of 2, and the square root of x squared is x. So in total, QB equals to square root of 2 times x. So the hypotenuse QB here equals to the square root of 2 times x. In the next step, I will present to you rule number 3, and we will implement rule number 3 in our drawing. According to rule number 3, the sum of the angles on one side of the straight line is equal to 180 degrees. So in the drawing we have the straight line AB. If we focus on the upper side of the straight line AB at point Q, where the sum of the angles must be equal to 180 degrees. So which angles we have at the upper side of AB at point Q? We have this angle alpha and this angle beta. So in total, alpha plus beta must be equal to 180 degrees. We can actually implement rule number 3 in our drawing. Why? Because in our drawing, if we focus on the upper side of the straight line AC, at point B, the sum of the angles here must be equal to 180 degrees. So I will copy the straight line AB with point B with its angles, and we will implement rule number 3 in this straight line AC. So this is the straight line AC that I copied from the original drawing. According to rule number 3, the sum of the angles on the upper side of the straight line AC at point B must be equal to 180 degrees. So which angles we have at the upper side of AC at point B? We have this angle that is equal to 45 degrees, plus the missing angle that we define as X, plus this angle that is equal to 45 degrees. In total, the sum of those three angles must be equal to 180 degrees. So 45 degrees plus 45 degrees is 90 degrees, so 90 degrees plus X, in total they must be equal to 180 degrees. Here we subtract 90 degrees from this equation, and finally we get that X, the missing angle X, equals to 180 degrees minus 90 degrees, that is 90 degrees. So this is a right angle, so you can write here that angle PBQ, the missing angle, is a right angle. And because of the fact that angle PBQ equals to 90 degrees, it means that triangle PBQ is a right angle. So we copy the right angle PBQ in a new page, and we will block this right angle triangle PBQ by a circle. We know that any triangle can be blocked by a circle, and especially triangle PBQ, that is a right triangle. So actually, this is the right triangle PBQ that I blocked by this circle. So in the drawing we have a circle. Inside this circle we have peripheral angle PBQ that is equal to 90 degrees. So I write it down, peripheral angle PBQ equals to 90 degrees in its size. And we have rule number 5 that relates to any peripheral angle that is equals to 90 degrees in its size. According to rule number 5, any peripheral angle that is equals to 90 degrees must rest on the diameter of the circle. In the drawing we have a circle. Inside this circle we have peripheral angle MAN. This peripheral angle MAN equals to 90 degrees in its size, and therefore according to this rule number 5, this peripheral angle MAN rests on the diameter of the circle. From the drawing it is very easy to see that peripheral angle MAN rests on chord MN, therefore chord MN is the diameter of the circle. It is very easy to see that indeed chord MN is the diameter of the circle. Why? Because of the fact that chord MN passes for point O, that is the center of the circle, and we know that any chord that passes for the center of the circle must be the diameter of the circle. So in conclusion, you can say that because of the fact that peripheral angle MN equals to 90 degrees, this peripheral angle MN rests on the diameter of the circle. That is to say, MN is the diameter of the circle. We can actually implement rule number 5 in our drawing. Why? Because in our drawing we have the peripheral angle QBP that is equal to 90 degrees, and therefore, according to rule number 5, this peripheral angle QPB rests on the diameter of the circle. It is very easy to see that peripheral angle QBP rests on chord QP, therefore, according to rule number 5, chord QP is the diameter of the circle. So if we define the radius of this circle as R, then the diameter QP must be equal to 2R. The diameter QP equals to 2R. From one side, but from the other side, we know that it is given us the equation that QS equals to QP. So if we define QS as X, then SP must be also equal to X because of the fact that they are equal to each other. So in total, QP equals to QS plus SP. That is to say, QP equals to QS, that is X, plus SP, that is X. So in total, QP equals to X plus X, that is 2X. So QP equals to 2X from one side, but from the other side, according to rule number 5, QP is also the diameter of the circle, that equals to 2R. And from those two equations, we will derive that 2X equals to 2R. Here we'll divide this equation by 2, and finally we get that X equals to R. So here X equals to R. So here SQ, that is X, it is equals to R, it is the radius of the circle, and PS, that is equal to X, it is equals to R. So here, so I will copy point S here, and found out actually that QS equals to R, and SP also equals to R. And because of the fact that those two radii of this circle touch each other at point S, we conclude from it that S is the center of the circle. S is the center of the circle. So we will join points S and B together by a straight line. Point S is the center of the circle, point B is the point of the circle itself, therefore SB is the radius of the circle, that is equals to R. So actually found out that PS equals to SB equals to SQ. All those three line segments are equal to each other, all of them. Each of them is the radii of this circle, therefore they are equal to each other. So here we join points S and B together by a straight line. Found out that SB equals to R, it is the radius of the previous circle, therefore SB equals to SQ. They are both the radii of the previous circle, therefore they are equal to each other. In the next step, we will do a construction. That is to say, we will complete this big quarter circle to a circle. So I copy the quarter circle to a new page and we complete the quarter circle to a circle. So actually, this is the quarter circle that I call it from the original drawing. SB equals to SQ, they are both the radii of the previous circle, therefore they are equal to each other. will join points Q and B together by a straight line. So I will complete this quarter circle to a circle. So I completed the quarter circle to a circle. In the next step, I will present to you a new rule, and we will implement the new rule in our drawing. The new rule is rule number 13. According to rule number 13, a central angle is twice as large as the peripheral angle subtended on the same arc. So in the drawing we have a circle. Inside this circle we have peripheral angle ASB. This peripheral angle ASB equals to theta in its size, and the peripheral angle ASB is subtended on arc AB. In addition, we have inside this circle the center angle AOB. This center angle AOB is subtended on the same arc, arc AB. So the peripheral angle and the center angle, they are both subtended on the same arc, arc AB. Therefore, according to this rule, rule number 13, the central angle will be twice as large as the peripheral angle that is subtended on the same arc, arc AB. And because of the fact that the peripheral angle ASB equals to theta, then the central angle AOB that is subtended on the same arc, arc AB will be equal to 2 theta. So we can actually implement rule number 13 in our drawing. Why? Because in our drawing we have the peripheral angle BSQ. This peripheral angle BSQ is subtended on arc BQ. And here we have also the central angle BCQ. The central angle BCQ is this angle. This central angle BCQ is subtended on the same arc, arc BQ. Therefore, according to rule number 13, the central angle BCQ must be twice as large as the peripheral angle BSQ. So what is the length of the central angle BCQ? We'll find out what is the length of the central angle BCQ according to rule number 6. According to rule number 6, the sum of the angles around a point will always add up to 360 degrees. So in the drawing we have point A. Here, according to this rule number 6, the sum of the angles around point A equals to 360 degrees. In order to prove this rule number 6, I drew a straight line that passes through point A. And here we have rule number 3. According to rule number 3, the sum of the angles on one side of a straight line is equal to 180 degrees. So if we focus on the upper side of this straight line at point A, here the sum of the angles must be equal to 180 degrees. Likewise, if we focus on the lower side of this straight line at point A, here the sum of the angles also must be equal to 180 degrees. So in total, the sum of the angles in the upper side of the straight line and the lower side of the straight line at point A will be equal to 180 plus 180, that is 360 degrees. So in conclusion, found out that the sum of the angles around point A in total it is equal to 360 degrees, exactly like this rule number 6. Actually, we can implement rule number 6 in our drawing. Why? Because in our drawing, if we focus at point C, the sum of the angles around point C in total it must be equal to 360 degrees according to rule number 6. So which angles we have around point C? Around point C we have this angle that is equal to 90 degrees plus the missing angle. In total the sum of those three angles must be equal to 360 degrees according to rule number 6. Therefore, this missing angle must be equal to 270 degrees. Why? Because 270 degrees plus 90 degrees, it is equal to 360 degrees, exactly according to rule number 6, that the sum of the angles around point C must be equal to 360 degrees. So the central angle BCQ equals to 270 degrees in its size. Therefore, the peripheral angle BSQ that is subtended on the same arc RBQ must be equal to half of it. That is to say, it must be equal to 270 degrees over 2, that is 135 degrees. So this angle equals to 135 degrees in its size. Peripheral angle BSQ equals to 135 degrees in its size. We will focus on the isosceles triangle, triangle BSQ. Triangle BSQ is an isosceles triangle because of the fact that side BS equals to side SQ. In the isosceles triangle BSQ, BS equals to SQ, and we have the rule that in front of equal sides in the triangle there are equal angles. So in front of those two equal sides, we have those two angles that must be also equal to each other. So if this angle is alpha, then the other angle must be also equal to alpha because they are equal to each other. And you also note that the sum of the angles in any triangle is equal to 180 degrees, and especially it is true in the associated triangle, triangle BSQ. So which angles we have in the associated triangle, triangle BSQ? We have alpha plus alpha, that is 2 alpha, plus 135 degrees. In total, the sum of those three angles must be equal to 180 degrees according to the rule that I mentioned. Here we will subtract 135 degrees from this equation, and we will get that 2 alpha equals to 180 degrees minus 180 degrees minus 135 degrees is 45 degrees. So 2 alpha equals to 45 degrees. We will divide this equation by 2, and finally we get that alpha equals to 45 over 2 degrees. So this angle alpha equals to 45 over 2 degrees. This is also angle alpha that is equal to 45 over 2 degrees. Okay, so in the next step, I will copy the right triangle, triangle PBQ in a new page here, and we will analyze this right triangle, triangle PBQ. So this is the right triangle, triangle PBQ that I covered from the original drawing. PB equals to the square root of 2 units. Side BQ equals to the square root of 2 times x units. And this is angle SQB is equals to alpha, that is actually 45 over 2 degrees. But angle SQB equals to angle PQB. Okay, so angle PQB equals to 45 over 2 degrees. So angle PQB, this angle PQB equals to 45 over 2 degrees in its size. So in this right triangle, triangle PQB, tangents 45 over 2 degrees equals to PB over QB. So tangents 45 over 2 degrees equals to PB, that is square root of 2, over qubit, that is square root of 2 times x. So here we have square root of 2 in the numerator and the square root of 2 in the denominator, so square root of 2 will get cancelled, and we're left here with 1 over x. So in conclusion, we found out that according to equation number 1, tangents 45 over 2 degrees equals to 1 over x. Okay. This is according to equation number 1. And we also have the trigonometric identity that states that tangents 2 theta equals to 2 tangents theta over 1 minus tangents square theta. We define angle theta is 45 over 2 degrees. If theta is 45 over 2, it means that 2 theta will be equal to 45 degrees. In the next step, we'll substitute theta by 45 over 2 degrees, and we'll substitute theta in this trigonometric identity by 45 degrees. And we'll get that according to equation number 2, tangents 2 theta is 45 degrees. Then it is equals to 2 times tangents theta. Theta is 45 over 2 degrees, according to our definition, over 1 minus tangents square, and theta is 45 over 2 degrees. So in conclusion, we found out that according to equation number 2, tangents 45 degrees equals to 2 times tangents 45 over 2 degrees over 1 minus tangents square 45 over 2 degrees. Tangents 45 degrees is 1, so 1 equals to 2 times tangents 45 over 2 degrees over 1 minus tangents square 45 over 2 degrees. Here we will define tangents 45 over 2 degrees as t, and we will substitute tangents 45 over 2 degrees in this equation number 2 by t. And you will get that according to equation number 2, 1 equals to 2 times tangents 45 over 2 degrees, and tangents 45 over 2 degrees according to our definition is t, over 1 minus tangents square 45 over 2 degrees. So if tangents 45 over 2 degrees is t, then tangent square 45 over 2 degrees will be equal to t square. So in total, in the denominator we have 1 minus t square. So in conclusion, found out that according to equation number 2, 1 equals to 2t over 1 minus t square. Here we'll multiply this equation number 2 by 1 minus t square, and we'll get that according to this equation number 2, 1 minus t square equals to 2t. Here we'll add to this equation number 2t square, and we'll get that 1 equals to t square plus 2t. Here we'll subtract 1 from this equation number 2, and finally we get that according to equation number 2, t squared plus 2t minus 1 equals to 0. So we actually found out that according to equation number 2, according to equation number 2, we found out that t squared plus 2t plus 1 equal t squared plus 2t minus 1 equals to 0. So this is a quadratic equation. And the general formula for a quadratic equation is ax squared plus bx plus c equals to 0. Here, in this general formula, a, b, and c are the coefficients of the quadratic equation, and x is the variable that we are looking for. And we'll find out the value of x according to the following formula. X equals to minus b plus minus square root of b squared minus 4 times a times c over 2a. In our specific quadratic equation, t squared plus 2t minus 1 equals to 0, the variable that we are looking for x is t, so x equals to t. The coefficient a equals to 1, the coefficient b equals to 2, and the coefficient c equals to minus 1. So we put the data inside the formula for x and we find out the value or the values of t, because x equals to t. So x equals to t, so we substitute x by t, and we get that t equals to minus b. b is 2, therefore minus b is minus 2 plus minus square root of b squared. b is 2, so b squared is 2 squared, that is 4, minus 4 times a is 1, times c, that is minus 1. All divided by 2 times a. a is 1, so it is 2 times 1. So here we found out actually that t equals to minus 2 plus minus square root, inside the root we have 4, minus 4 times minus 1 is plus 4, so in total inside the root we have 4 plus 4, that is 8 over 2. So actually we found out that t equals to minus 2 plus minus the square root of 8. 8 is 4 times 2, so we substitute 8 by 4 times 2 divided by 2. So t equals to minus 2 plus minus the square root of 4 is 2, so inside the root we left only with 2. So t equals to minus 2 plus minus 2 times square root of 2 over 2. So actually found out that t equals to minus 2 over 2 is minus 1, plus minus 2 over 2 is 1. So in total this expression equals to square root of 2. So in conclusion, we actually found out that t equals to minus 1 plus minus square root of 2. So here we have two solutions that are possible for t. The first solution for t is that t equals to minus 1 minus square root of 2. And the second solution that is possible for t is that t equals to minus 1 plus square root of 2. So according to the first solution, t equals to minus 1 minus square root of 2. Minus 1 minus square root of 2, it is a negative number, so t is a negative number. But according to our definition, t equals to tangents 45 over 2 degrees. That is a positive number. So a negative number can never be equal to a positive number. Therefore, this solution is not correct. We'll cancel this solution and we left if only the second solution that is possible for t, that t equals to minus 1 plus square root of 2. So according to our definition, t equals to tangents 45 over 2 degrees. So tangents 45 over 2 degrees, that is t, is equals to square root of 2 minus 1. This is according to equation number 2. Again, according to equation number 2, we actually found out that tangent 45 over 2 degrees equals to square root of 2 minus 1, while according to equation number 1, we have already found out that tangent 45 over 2 degrees equals to 1 over x. So I show you again, we have, according to equation number 1, we have already found out that tangent, this is equation number 1, we already found out that tangent 45 over 2 degrees and tangent 45 over 2 degrees equals to 1 over x. Here, according to equation number 1, we have already found out that tangent 45 over 2 degrees equals to 1 over x. Okay. So we have two different equations for the value of tangent 45 over 2 degrees. Therefore, we'll create equation number 3. According to equation number 3, tangent 45 over 2 degrees, according to equation number 1, must be equal to tangent 45 over 2 degrees, according to equation number 2. So tangent 45 over 2 degrees, according to equation number 1, is 1 over x, and it must be equal to tangent 45 degrees over 2. It must be equal to tangent 45 over 2 degrees according to equation number 2. And tangent 45 over 2 degrees according to equation number 2 is square root of 2 minus 1. So in conclusion, we found out that according to equation number 3, 1 over x equals to square root of 2 minus 1. Here we multiply this equation by x and we get that according to equation number 3, 1 equals to x times square root of 2 minus 1. Here we divide this equation number 3 by square root of 2 minus 1. And we get that according to equation number 3, x equals to 1 over square root of 2 minus 1. Repeat again. We actually found out that x equals to 1 over square root of 2 minus 1. So here we focus on this side of the equation and we will multiply the numerator by square root of 2 plus 1, and then we divide this side of the equation by square root of 2 plus 1. So x equals to 1, we multiply the numerator by square root of 2 plus 1, and then we divide it by square root of 2 plus 1. So we change nothing. We actually multiply it by 1. It is allowable to multiply everything by 1. So we have here square root of 2 minus 1. So we multiplied 1 over square root of 2 minus 1 by square root of 2 plus 1, and then we divide it by square root of 2 plus 1, so we change nothing. So actually found out finally that x equals to the square root of 2 plus 1 over square root of 2 minus 1 times square root of 2 plus 1 equals to, according to the algebraic identity, that a minus b times a plus b equals to a squared minus b squared. We'll get that the expression square root of 2 minus 1 times square root of 2 plus 1 will be be equal to the square root of 2 squared, that is 2, minus 1 squared, that is 1. So in conclusion, we found out that x equals to the square root of 2 plus 1 over 1, that is square root of 2 plus 1. So x equals to either square root of 2 plus 1 units, or in terms of numbers, x equals to 2.414 units. Repeat again, we found out actually that the length of line segment BC that is equals to x is equals to either square root of 2 plus 1 units, or in terms of numbers, BC that is equal to x, it is equals to 2.414 units. And that is the answer to the question. In the next step, I will summarize the lecture. In this lecture, we found out the length of this line segment BC is equal to x. So, in the drawing, we have those two quarter circles. We know that AB equals to 1 unit in its length. Line segment QS equals to line segment SP. And our mission is to find out the length of this line segment BC that is equal to x. So, first of all, because of the fact that this is a quarter circle, AB must be equal to PA, they are both the radii of this quarter circle, therefore they are equal to each other. But AB equals to 1, therefore PA must be also equal to 1. Then we join points P and B together by a straight line. In this way we created the right triangle PAB, so I copied the right triangle PAB in a new page and implemented the Pythagoras theorem in this right triangle PAB. So this is the right triangle PAB that I copied from the original drawing. Here by PT is the evaluation for Pythagoras theorem. According to the Pythagoras theorem, in this right triangle PAB, PB squared equals to PA squared plus AB squared. So PB squared, that is the square of the hypotenuse, equals to PA squared. PA is 1, therefore PA squared is 1 squared, that is 1, plus AB squared. AB is 1, so AB squared is 1 squared, that is 1. So in total PB squared equals to 1 plus 1, that is 2. PB squared equals to 2. We took a root out of this equation and finally found out that PB equals to the square root of 2. Here, the hypotenuse PB equals to the square root of 2 units in its length. So, we focused on the right triangle PAB. In the right triangle PAB, PA equals to AB. And we have the rule that in front of equal sides in the triangle there are equal angles. So those two angles that are located in front of those two equal sides must be equal to each other. So if this angle is alpha, then the other angle must be equal to alpha, because they are equal to each other. And you also know that the sum of the angles in any triangle, and especially in triangle PAB, must be equal to 180 degrees. So which angles we have in the right triangle PAB? We have angle alpha plus alpha, that is 2 alpha plus 90 degrees. In total, it must be equal to 180 degrees. Repeat again. In the right triangle PAB, 2 alpha plus 90 degrees must be equal to 180 degrees. We subtract the 90 degrees from this equation, and finally we found out that 2 alpha equals to 180 degrees minus 90 degrees it is 90 degrees. So 2 alpha equals to 90 degrees. We divided the equation by 2 and finally found out that alpha equals to 90 degrees over 2, that is 45 degrees. So this is an angle alpha that is equals to 45 degrees in its size, and this angle alpha also equals to 45 degrees. Likewise, then we join points Q and B together by straight line. So in this quarter circle, BC must be equal to CQ. They are both the radii of this quarter circle, therefore they must be equal to each other. But BC is x, therefore QC must be also equal to x. And so in the right triangle QBC, those two angles, each of them must be equal to 45 degrees. If we repeat on the same process that we did in the right triangle PAB, we will arrive to the conclusion that those two angles, each of them is equal to 45 degrees in its size. Okay, then I copied the right triangle QBC in a new page and we implemented the Pythagoras theorem on this right triangle, triangle QBC. This is the right triangle QBC that I copied from the original drawing. Here by PT is the evolution from Pythagoras theorem. In this right triangle QBC, QB square equals to BC square plus QC square. So QB square, that is the square of the hypotenuse, equals to QC square. QC is x, therefore QC square is x square plus BC square. BC is x, therefore BC square is x square. So in total, QB square equals to x square plus x square, that is 2x square. So QB square equals to 2x square. We took out of this equation and finally found out that QB, that is the length of the hypotenuse QB, equals to the square root of 2x square. The square root of 2x square is the square root of 2, and the square root of x square is x. So in total, QB equals to square root of 2 times x. Here, the hypotenuse QB equals to the square root of 2 times x. Okay, then I presented to you rule number 3 and implemented rule number 3 in our drawing. According to rule number 3, the sum of the angles on one side of a straight line is equal to 180 degrees. So in the drawing we have the straight line AB. If you focus on the upper side of the straight line AB at point Q, here the sum of the angles must be equal to 180 degrees according to this rule, rule number 3. So which angles we have at the upper side of AB at point Q? We have this angle alpha and the other angle that is beta. So in total alpha plus beta must be equal to 180 degrees according to this rule, rule number 3. Actually, we can implement rule number 3 in our drawing. Why? Because in our drawing, if you focus on the upper side of the straight line AC at point B, here the sum of the angles must be equal to 180 degrees. So I copied the straight line AB with point B in a new page, and we implemented rule number 3 in the straight line AC. This is the straight line AC, and this is point B. We know that the sum of the angles on the upper side of the straight line AC at point B must be equal to 180 degrees. So which angles we have at the upper side of AC at point B? We have this angle that is 45 degrees plus the missing angle that we define as x plus this angle that is equal to 45 degrees. In total, the sum of those three angles must be equal to 180 degrees according to rule number 3. So 45 degrees plus 45 degrees is 90 degrees. So in total, in this side of the equation, we have 90 degrees plus x is equal to 180 degrees. We subtracted 90 degrees from this equation and finally found out that x, the missing angle x, equals to 180 degrees minus 90 degrees, that is 90 degrees. So this angle ABQ, that is equal to x, it is a right angle. It is equal to 90 degrees in its side. Then I copied the right triangle. So because of the fact that angle PBQ is a right angle, therefore triangle PBQ is a right triangle. Then I copied the right triangle PBQ in a new page, and we blocked this right triangle, triangle PBQ. We know that any triangle can be blocked by a circle, and especially by the right triangle PBQ. So this is the right triangle, triangle PBQ that are blocked by this circle. So in this drawing we have a circle. Inside this circle we have peripheral angle PBQ that's equal to 90 degrees. And we have here rule number 5 that relates to any peripheral angle that's equal to 90 degrees. according to rule number 5, any peripheral angle that is equal to 90 degrees must rest on the diameter of the circle. In the drawing we have a circle. Inside this circle we have peripheral angle MAN. This peripheral angle MAN equals to 90 degrees in its size, and therefore according to this rule number 5, this peripheral angle MAN must rest on the diameter of the circle. And indeed it is very easy to see that peripheral angle MAN rests on the diameter of the circle. Why? Because peripheral angle MAN rests on MN, and MN, chord MN, is indeed the diameter of the circle. Why? Because of the fact that chord MN passes through point O, that is the center of the circle. We know that any chord that passes through the center of the circle must be the diameter of the circle. So in conclusion, we found out that because of the fact that peripheral angle MAN equals to 90 degrees, therefore it rests on the diameter of the circle. MN is the diameter of the circle. We can actually implement rule number 5 in our drawing. Why? Because in our drawing we have the peripheral angle. We have peripheral angle PQB is equal to 90 degrees in its side. Therefore, peripheral angle PBQ equals to 90 degrees in its side. Therefore, according to rule number 5, this peripheral angle PBQ rests on the diameter of the circle. From the drawing, it is very easy to see that peripheral angle PBQ rests on chord PQ. Therefore, chord PQ, according to rule number 5, it is the diameter of the circle, or chord QP is the diameter of the circle. So if we define the radius of this circle as R, if the radius of the circle equals to R, again, if the radius of this circle equals to R, then the diameter QP must be equal to 2R. So from one side, QP equals to 2R. But from the other side, we have here QP. It is given us the equation that QS equals to SP. So if QS is X, then SP also equals to X because they are equal to each other. So in total, QP equals to QS, that is X, plus SP, that is also X. So in total, QP equals to X plus X, that is 2X. So from the other side, QP equals to X. From one side, QP is the diameter of the circle, therefore it is equals to 2R. From the other side, QP equals to 2X. From those two equations, we derive that 2X equals to 2R. We divided this equation by 2 and finally found out that X equals to R. So X equals to R. So here, PS that is equals to X equals to R, and SQ that is also equals to X, it is equals to R. So here, PS equals to R and QS equals to R. Okay? And because of the fact that those two radii touch each other at point S must be the center of the circle. Here, point S is the center of the circle. Then we join points S and B together by straight line. Point S is the center of the circle, point B is the point of the circle itself, therefore SB is the radius of the circle that is equal to R. So actually, in conclusion, found out that PS equals to SQ equals to SB. Those three line segments are equal to each other because of the fact all those three line segments are the radii of this circle, therefore they are equal to each other. So here, PS equals to R, SQ equals to R, and SB also equals to R. Okay, then we did a construction, that is to say, we completed this big quarter circle to a circle. So copied this quarter circle to a new page and we completed it to a circle. Actually, this is the quarter circle that I copied from the original drawing. Then I completed this quarter circle to a circle. Again, we have already found out that QS equals to QB equals to R. They are both the radii of the previous circle, therefore they are equal to each other. Okay. and then I presented to you rule number 13, and we implemented rule number 13 in our drawing. According to rule number 14, a central angle is twice as large as the peripheral angle subtended on the same arc. So in the drawing we have a circle. Inside this circle we have the peripheral angle ASB. Peripheral angle ASB equals to theta. And this peripheral angle ASB is subtended on arc AB. In this drawing we have also another angle. We have the central angle AOB. This central angle AOB is subtended on the same arc, arc AB. So whenever you have a peripheral angle and the central angle inside the circle, that both of them are subtended on the same arc, then the central angle must be twice as large as the peripheral angle. And because of the fact that this peripheral angle is ACB equals to theta in its size, therefore the peripheral angle AOB that's subtended on the same arc, arc AB, must be equal to 2 theta. We can actually implement rule number 13 in our drawing. Why? Because in our drawing we have this peripheral angle QSB. Peripheral angle QSB is subtended on arc QB. And here we have the central angle QCB. This central angle QCB, this is the central angle QCB. This central angle QCB is subtended on the same arc, arc BQ. Therefore, we have a central angle that is subtended on the same arc as the peripheral angle. Therefore, according to rule number 13, the central angle must be twice as large as the peripheral angle that's subtended on the same arc. That is to say, the central angle BCQ must be twice as large as the peripheral angle BSQ. In order to find out the size of the central angle BCQ, this angle I presented to you rule number 6, and we implemented rule number 6 in our drawing. According to rule number 6, the sum of the angles around a point will always add up to 160 degrees. So in the drawing we have this point, point A. According to rule number 6, this rule number 6, the sum of the angles around point A must be equal to 360 degrees. In order to prove that this rule is true, I draw this straight line. This straight line passes for point A. And here we have rule number 3. According to rule number 3, the sum of the angles on one side of a straight line is equal to 180 degrees. So if we focus on the upper side of this straight line in point A, the sum of the angles on the upper side in point A must be equal to 180 degrees. Likewise, if we focus on the lower side of this straight line at point A, the sum of the angles must be also equal to 180 degrees. So, in total, the sum of the angles in the upper side of the straight line at point A and in the lower side of this straight line at point A, it also equals to 180 degrees. So in total, the sum of the angles in the upper side, that is 180 degrees, plus the sum of the angles in the lower side of this straight line at point A, this is also 180 degrees, it is equal to 360 degrees, exactly according to this rule that the sum of the angles around any point is equal to 360 degrees. Okay, we actually proved that rule number 6 is true. So we can actually implement rule number 6 in our drawing. Why? Because in our drawing we have, if we focus at point C, according to rule number 6, the sum of the angles around point C must be equal to 360 degrees. So which angles we have at around point C? We have this angle that's equal to 90 degrees plus the missing angle. In total, they must be equal to 360 degrees according to rule number 6. Therefore, this missing angle must be equal to 270 degrees. Why? Because 270 degrees plus 90 degrees, it will be equal to 360 degrees. That is the sum of the angles around point C according to rule number 6. So therefore, the missing angle equals to 270 degrees. That is to say, the size of the central angle QCB is 270 degrees. And this central angle QCB is subtended on chord QB. Therefore, it must be twice as large as the peripheral angle QSB that is also subtended on the same arc QB. Therefore, if the central angle equals to 270 degrees, it means that the peripheral angle that is subtended on the same arc QB, must be equal to 270 degrees over 2, that is 135 degrees. So in conclusion, we found out that the peripheral angle QSB equals to 135 degrees in its size. Then in triangle QSB, you know that QS equals to SB. Therefore, triangle QSB is an isosceles triangle. So those two sides are equal to each other, and we have the rule that in front of equal sides in the triangle there are equal angles. So those two angles that are located in front of those two equal sides must be also equal to each other. So if this angle is alpha, then the other angle must be also equal to alpha because they are equal to each other. And we also note that the sum of the angles in any triangle is equal to 180 degrees, and especially it is true in the isosceles triangle QSB. So the sum of the angles in the isosceles triangle QSB is equal to 180 degrees. So which angles we have inside triangle QSB? We have alpha plus alpha, that is 2 alpha, plus this angle that is 135 degrees. In total, they must be equal to 180 degrees according to the rule that I mentioned. Here we subtract 135 degrees from this equation, and finally we get that 2 alpha equals to 180 minus 135 degrees, that is 45 degrees. So 2 alpha equals to 45 degrees. We divided this equation by 2 and finally found out that alpha equals to 45 over 2 degrees. So this is angle alpha that is equals to 45 over 2 degrees in size, and this is also angle alpha that is equals to 45 over 2 degrees in its size. Then I copied the right triangle QPB in Olympiad and analyze this right triangle QPB. This is the right triangle QPB that I copied from the original drawing. Side PB equals to the square root of 2 units, side QB equals to the square root of 2 times x units, and this angle BQS or BQP, doesn't matter, equals to 45 over 2 degrees. So this is angle BQP that is equal to 45 over 2 degrees. So in this right triangle BQ, triangles 45 over 2 degrees equals to PB over BQ. Again, triangles 45 over 2 degrees equals to PB over BQ. PB is square root of 2, BQ is square root of 2 times x. So we have square root of 2 in the numerator and square root of 2 in the denominator, so square root of 2 will get cancelled, and we left with only 1 over x. So in conclusion, we found out that according to equation number 1, tangents 45 over 2 degrees equals to 1 over x. Tangents 45 over 2 degrees equals to 1 over x. This is according to equation number 1. While we have actually also trigonometric identity. We have the trigonometric identity that states that tangents 2 theta equals to 2 tangents theta over 1 minus tangents square theta. We defined theta as 45 over 2 degrees. If theta is 45 over 2 degrees, it means that 2 theta is 45 degrees. Then we substituted theta in this trigonometric identity by 45 over 2 degrees, and we substituted 2 theta by 45 degrees. And we found out that according to this trigonometric identity, tangents 2 theta is 45 degrees equals to 2 times tangents theta, and theta is 45 over 2 degrees, over 1 minus tangents square theta. So it is tangents square theta, and theta is 45 over 2. So in conclusion, we found out that according to equation number 2, tangents 45 degrees equals to 2 times tangents 45 over 2 degrees over 1 minus tangent square 45 over 2 degrees. Here tangents 45 degrees is 1, and it is equals to 2 times tangents 45 over 2 degrees over 1 minus tangents square 45 over 2 degrees. Then we define the tangents 45 degrees minus 45 over 2 degrees is t, and we substitute minus 45 over 2 degrees in this equation number 2 by t. So here we get that according to equation number 2, 1 equals to 2 times minus 45 over 2 degrees, and minus 45 over 2 degrees is t. So we substitute it by t. So in the numerator of this side of the equation we have 2t over 1 minus tan square 45 over 2 degrees. If tan 45 over 2 degrees is t, then tan square 45 over 2 degrees will be equal to t squared. So in total, in the denominator we have 1 minus t squared. So according to equation number 2, 1 equals to 2t, 1 equals to 2t over 1 minus t squared. Here we multiply this equation number 2 by 1 minus t squared, and found out that according to equation number 2, 1 minus t squared equals to 2t. Okay, here we added t squared to this equation number 2, and finally found out that 1 equals to t squared plus 2t. Here we subtracted 1 from this equation number 2, and found out that t squared plus 2t minus 1 equals to 0. Repeat again. We found out that according to equation number 2, t squared plus 2t minus 1 equals to 0. So this is a quadratic equation, and the general formula for a quadratic equation is ax squared plus bx plus c equals to 0. Here a, b, and c are the coefficients of the quadratic equation, and x is the variable that we are looking for. And we'll find out the value of x according to the following formula. X equals to minus b plus minus square root of b squared minus 4 times ac over 2a. In our specific quadratic equation, t squared plus 2t minus 1 equals to 0, the variable that we are looking for is t, so x equals to t. The coefficient a equals to 1, the coefficient b equals to 2, and the coefficient c equals to minus 1. So we put the data inside this formula and found out the value of the values of t, because x equals to t. So we substitute x by t. So t equals to minus b. b is 2, therefore minus b is minus 2, plus minus square root of b squared. b is 2, therefore b squared is 2 squared, it is 4, minus 4 times a is 1, times c, that is minus 1 over 2 times a is 1, so it is 2 times 1. So conclusion found out that t equals to minus 2 plus minus, inside the root we have 4, and minus 4 times minus 1 is plus 4. So in total, inside the root we have 4 plus 4, that is 8, divided by 2. So t equals to minus 2 plus minus square root of 8 over 2. T equals to minus 2 plus minus 8 is 4 times 2, so we substitute 8 by 4 times 2 divided by 2. So t equals to minus 2 plus minus the square root of 4 is 2, so inside the root we left only with 2. So in total we actually found out that t equals to minus 2 plus minus 2 times square root of 2 over 2. Minus 2 over 2 is 1, and 2 over 2 is 1. So in conclusion we found out actually that t equals to minus 1 plus minus square root of 2. So here we will have two solutions that are possible for t. The first solution for t is that t equals to minus 1 minus square root of 2. And the second solution that is possible for t, is that t equals to minus 1 plus square root of 2. According to the first solution for t equals to minus 1 minus square root of 2. Minus 1 minus square root of 2 is a negative number, but according to our definition, t equals to minus 45 over 2 degrees. This is a positive number. And a positive number can never be equal to a negative number. Therefore, we cancel this solution, and we left only with the second solution that is possible for t, that t equals to minus 1 plus square root of 2. And according to our definition, t equals to minus 45 over 2 degrees. So this equation is equation number 2, and according to equation number 2, minus 45 degrees over 2 equals to square root of 2 minus 1. This is according to equation number 2. While according to equation number 1, again according to equation number 2, minus 45 over 2 degrees equals to square root of 2 minus 1. While according to equation number 1, we have already found out that tan 45 over 2 degrees equals to 1 over x. So we have two different equations for tan 45 over 2 degrees. Therefore, we created equation number 3 that states that tan 45 over 2 degrees according to equation number 1 must be equal to tan 45 over 2 degrees according to equation number 2. Tan 45 degrees over 2, tan 45 over 2 degrees according to equation number 1 is 1 over x, and it must be equals to tan 45 over 2 degrees according to equation number 2, that is actually square root of 2 minus 1. So in conclusion, it's found out that according to equation number 3, 1 over x equals to the square root of 2 minus 1. Here we multiply this equation by x and found out that 1 equals to x times square root of 2 minus 1. Here we divided this equation number 3 by square root of 2 minus 1, and finally found out that x equals to 1 over square root of 2 minus 1. Then we focus on this side of the equation and we multiply this side of the equation by square root of 2 plus 1, and then we divide it by square root of 2 plus 1. Square root of 2 plus 1 over square root of 2 plus 1 is 1. And it is allowable to multiply anything by 1. So this operation is allowable. So x equals to square root of 2 plus 1 over square root of 2 minus 1 times square root of 2 plus 1. Okay? So in the numerator we have x that is equal to square root of 2 plus 1. And this expression square root of 2 minus 1 times square root of 2 plus 1 is equal, according to the algebraic identity, that a minus b times a plus b equals to a squared minus b squared. This expression equals to the square root of 2 squared, that is 2, minus 1 squared, that is 1. So in total, this expression equals to 2 minus 1, that is 1. So actually we found out that x equals to the square root of 2 plus 1. X equals to either square root of 2 plus 1 units in its length. On terms of numbers, x equals to 2.414 units. I repeat again, the length of this line segment BC is equal to x. It is equal to either square root of 2 plus 1 units. On terms of numbers, the length of this line segment BC is equal to x. It is equal to 2.414 units. Okay, thank you very much.